We've all been there. I need to take this unit and move it to this location on a NavMesh. I'll just call NavMesHagent.SetDestination to that target location. Done! That works fine for a lot of use cases, but as you start getting more complex mechanics into your game, you'll probably find that you need some more advanced usage other than just set destination to the target position. In this video, you'll learn some more advanced techniques using the NavMesh, such as finding the closest point on a NavMesh, raycasting on the NavMesh, and even checking distances across different NavMeshes. Hey, Chris here from LlamAcademy. Here to help you. Ooh, me? Yes, you! Make your game dev dream become a reality by helping you get more mileage out of your NavMeshes. I ran into multiple challenges with the NavMesh and NavMesh agencies while making this free and open source microgame, Dino Attack. Full project on GitHub, full game on itch, both are free. The level is constructed where we have enemy defenders that are up on a high platform. And I didn't want them to come down and just get eaten alive by dinosaurs, so I set up a NavMesh surface where they can basically only be on top of these platforms, and then have a walkway in the back where they can go if one of them gets destroyed. That way they can always get around from tower to tower. And these guys have relatively large sensor ranges to detect when dinosaurs are coming, and then I wanted them to start going that direction to defend the tower. But if they can never get onto the ground where the dinosaur is, we can't just call NavMesHagent.SetDestination to the dino's position. That will always fail to set a path because there's no way that that unit can ever get to that point where the dinosaur is. And we don't want them to, because if they climb down and walked over there, they just get eaten alive by the velociraptors. Not good, not smart. So when we have this type of scenario, which is a pretty common use case, I think, it's really a two-part solution. We first have to make sure that we construct the level and set up our NavMesh surfaces and NavMesh modifiers, NavMesh modifier volumes, to restrict them to only walk in those areas. If all of that's Greek to you, I've got full detailed breakdowns of how all these different components work in the AI series, and I'll have links in the description to those. Basically, these are the high-level components that we use from the navigation package to say these agents can walk in these specific areas. The second component is we want to update our set destination logic to not just say, move to the target location. Instead of setting the destination to the dino's position, we need to pick a new location that will take us in the direction that we want to go to be able to attack them without leaving our area. To keep that behavior where we're making sure we're still staying on our NavMesh and moving in the direction we want to move, we can use the NavMesh.Raycast. And these enemies are using Unity behavior to control what they do. So the movement is handled in a custom move to target or edge of NavMesh action. If you're not super familiar with Unity behavior, I've got a little mini series here on YouTube where we cover all the basic components you need to know to use this first-party behavior tree solution from Unity. Link in the description. On start is called as soon as the behavior tree decides it wants to go to this node or this action. We start off with just some simple validation, which is a standard pattern that I usually follow in these actions to make sure we have all the right components hooked up in Unity behavior. Then we're simply getting a convenient reference to our own transform and the target's transform, that's the dino that we want to currently attack. Then we make a NavMesh query filter, which gives us more granular control when we're sampling the NavMesh. Typically, when you do something like NavMesH.Raycast or NavMesH.Sample.Position, you historically just said, give me an area mask. But now we can have multiple types of units. So this NavMesh query filter is a struct that allows us to say, for this agent type and these area masks, sample the NavMesh. This gives us control to say, only sample where this type of unit can walk, not just a walkable location on the NavMesh. Then we're doing something that's very similar to what we may commonly do. We may typically do something like if NavMesH.Sample.Position, providing a target location, get out a hit, give it the max distance to sample, and give it a query filter. This probably looks familiar if you've used the navigation system before. However, we've already said that this is not what we want to do. So the NavMesH.Raycast behaves very similarly to how you may think it would work, where you provide a start location, a target location, give it out that edge hit in the query filter, and this will work exactly like it sounds. It will shoot a ray on the NavMesh from the self-transform position to that target position. If it hits any edge of the NavMesh, it'll populate that NavMesh hit, edge hit, while it's using this query filter. And importantly, this will follow the NavMesh if the NavMesh has any height difference. So it only hits the edge of a NavMesh. This means that the raycast will always tell us, if it hits something, where the agent can run to before they hit a problem where they can't move any closer, if they're running in a straight line towards a specific point. And for our use cases, this is the most common flow to take. But because velociraptors can come up on top, it's possible that this would fail because there's no edge between our unit and the velociraptor. That's why we have the else case where we'll just set that destination to the target position. Then we return, hey, we're running, because we know that we're going to try to move. Then on update, which is called once per time the graph updates, which is typically once per frame, we find out if we're in the attack range. If we are, we'll turn, hey, we're done. If we're pending a path or something like that, we'll just return, hey, we're still running. And once per frame, then we're doing this sample position raycast stuff that we just did on start, making sure that we're setting that destination. And another thing that you may need to worry about is if there's not an edge hit. That just means that there's no edge to move towards, but we can't sample the position. We can move towards the target by setting the agent velocity, by getting the direction towards that enemy, and then just overriding the agent velocity towards that enemy. This gives us the ability to still move, even if we can't sample a position where the enemy currently is, and our NavMesh can't find an edge. This is an unlikely scenario, but this was included as a fallback just in case something didn't work out right. We didn't want the AI just to stand still. So the NavMesh.Raycast gives us the edge with a specific position on that edge that's in the direction of a target that we want to move towards. And the API for it is extremely similar to our NavMesh sample position. This is all coming from my free and open source microgame Dino Attack, which I just released, that I made specifically to teach some of these concepts. You can play it for free on itch, and you can get the full project code for free on GitHub. A special shout out to polyperfect, who's provided basically all the art assets you see in this game under an educational use only license, which means basically you can't use these for anything other than playing around. If you do like them and you want to use them in your game, check out my affiliate link down in the description to support polyperfect to buy those assets. Also, if you love this concept, make sure you hit that like button to help this video and this project reach more people. Next, the T-Rex had basically the inverse problem of those defenders. The T-Rex can never get on top of those buildings, and it doesn't need to because it's so massive. What the T-Rex needed to do was walk up until it comes in attack range of whatever it's trying to eat and just eat them off the top without having to get onto the other NavMesh. So again, setting NavMesHAgent.SetDestination to the defender's target position didn't really make sense because the T-Rex would never be able to reach that location. And using the NavMesh.Raycast also assumes that there will never be anything in between where I am and where I'm trying to go, except for the edge that I want to hit, which is not true in more complex world environments, or even in this game with a very simple world environment if the T-Rex is coming from some of the sides. So we've got a class move to closest attackable on XZ plane action, which is again a Unity action. It just has ourself and the target object. And I structure this one a little bit differently. And so you can see here, we just do the same validation stuff, make sure we have all the right components. And then we're saying target location, which is a vector 3, get target location. And then we set the destination to that location. However, get target location is where all the magic happens. It's a relatively large function. We try to get the closest point on the collider. Otherwise, we just use the target object transform position. The dinos have the added complexity here where we're considering closest points on colliders because they can attack both units and buildings. The buildings have their origin at the center of the mesh, which will not be super close to a valid NavMesh location. Picking the closest point on the collider allows us to do a smaller NavMesh sample position and guarantees that the position picked will be on the side that the dino can reach. We reset the Y to be our current Y, so again, we're ignoring the Y axis. We still create that query filter. We do both a raycast and a sample position. If the raycast hit or the sample position hit, then we say get closest hit, which is just a vector 3 distance comparison, including whether something hit or not. So if only hit 1 hit, we're using hit 1. If only hit 2 hit, we're using hit 2. Otherwise, we do that distance comparison and return either hit 1 or hit 2. So once we know that hit, we're setting the target location to be the hit position. Then we get the direction towards that hit position from our current position and subtract out the agent's radius amount in that direction so we know the right place to stop. Then remember that ends are on start after we set the destination. We say we're running, then we come back to update, where we again just find out, hey, what's a new target location? And if the distance has meaningfully changed, meaning that the distance between the new and the target location are greater than or equal to the agent stopping distance, then we'll move. We'll set that destination again and set our target location to that new target location. If it hasn't meaningfully changed, we check, are we at that location? If so, we'll return success. Otherwise, we say we're running. And is that target location is a utility function I made, which is kind of long because there's a compound formula to detect if we're currently at the position, because if we don't have a path and the path is not pending, that means we are at the location. But if we have a path, then we need to check the remaining distance and compare that to our stopping distance and our radius. And if the remaining distance is less than that, then we know we're at the location. While we generally like to have reusable as possible movement code, we can see that our enemy units have somewhat different movement requirements than some dinos. The core takeaway here is that we have options for how we pick a location to move to, and simply setting a destination to a target game object's position may not be good enough for some use cases. A combination of a sample position with a relatively large radius, coupled with a raycast, or even setting a velocity and checking for edges with raycasts may give you better movement. And again, if you got value out of this video and you love this concept, make sure you've liked and subscribed to help this video and this project reach more people. And another huge shout out for polyperfect for giving these art assets. It's just a lot more fun to work in a game that looks like a game instead of just prototype stuff. So show them some support too, pick up some of these assets if you think they look awesome and they might help you in your game. Other ways you can show your support for LlamAcademy is you can get yourself some LlamAcademy merch right here on YouTube. It's actually my favorite shirt. You can pick up my RTS course. That's 24 plus hours of lecture content where we walk through you step by step how to make your very own RTS game. You can also become a YouTube member or a Patreon supporter. Your recurring contribution there helps out tremendously, and you'll get your name in the GitHub repository and up here on the screen at the end of every video. You'll get access to a private members exclusive Discord with some behind the scenes updates. Starting at the awesome tier, you'll also get a shout out at the end of every video, like Ivan, Iphiobulus, Jason Hansen, Snedden, Trey Briggs, Will B, Mustafa, Nick5454, and Pixel Wizards. There's also all of these great supporters as well. Thank you all for your support, and I'll see you on the next video.